Yeah, works. Good afternoon, everyone. Welcome to the session on LWE and its applications. We have three talks. The first one is by Matthias Johann Steiner about the complexity of algebraic algorithms for LWE.
Okay, so hello. This talk is about attacking learning with errors with polynomial system solving. So I'm pretty sure most people in this room have heard about this learning with errors problem. It's quite famous in cryptography. So we fix a modulus Q, and for us Q always will be a prime number, so we work over a finite field. And then we fix some integer dimension n, and we pick a probability distribution over the integers. And then we pick a secret vector S, and now we generate an LWE sample as follows. We generate a new random vector A, and then we compute the scalar product of the secret with A, add a random error E, drawn with the probability distribution, and then compute modulo Q. And then release the vector A together with the result B. And now the search LWE problem, well, simply speaking, I give you multiple LWE samples, give me back the secret vector S. Yeah, and the typical choice for the probability distribution is like a discrete Gaussian, but to keep things simple, in the paper we work with the Gaussian heuristics, so treating it as a Gaussian in the asymptotic setting. And yeah, the first polynomial system to tackle search LWE was proposed by Aurora G. So you fix an integer interval, and then you set up an error polynomial, which has all roots in this integer interval. And the idea is you make this interval big enough, and then with decent probability, all your errors from LWE samples will fall into this interval. So now, given an LWE sample A and B, you set up a variable vector x representing the secret, and then you substitute B minus the scalar product of x with A into the error polynomial. And then, as I said before, provided this interval is big enough, with decent probability under the Gaussian heuristic, the true secret will be a root of this polynomial. And now, okay, you have multiple samples, you can set up multiple such multivariate polynomials. Now, to solve for the secret, essentially you have to solve for x. And Aurora G, they proposed to solve the polynomial system with linearization. And later, Albrecht et al., they generalized this approach to Grübner basis computation. But to devise complexity estimates, they assumed that LWE polynomial systems are semi-regular, well, because semi-regular systems have a nice theoretical complexity bound. Yeah, and this, so our work, or my work, can be thought like as a continuation of the analysis of Albrecht et al. But in this work, we try to drop the semi-regularity assumption. Then the question is, can we still derive complexity estimates for Grübner basis computations? And well, the answer is yes. So in the paper, we have like a full proven complexity estimate on almost all LWE instances. But this will come at a cost, so this complexity estimate will turn out to be exponential in the dimension of the secret. But previous analysis, like Albrecht et al., they have reported sub-exponential complexity estimates under the semi-regularity assumption for certain LWE instances. So and to bridge this gap between a proven, theoretical exponential estimate and previously reported semi-regular estimates, in this paper we propose a heuristic worst-case scenario framework from a designer's perspective. So worst-case means like within theoretical provable bounds, we propose a worst-case framework that, under minimal assumptions, can achieve sub-exponential complexity estimates for certain LWE polynomial systems when everything goes wrong. And as a last contribution in this paper, we discuss how one can incorporate mathematical hints coming from potential side information, like a side channel, into a polynomial system and how it might affect the complexity of solving your overall system. So now I'm going to shortly recall what a Grübner basis is. So we take a polynomial ring in n variables over a field. Yeah? And then a monomial, well, it's a product of variables, and we can associate a monomial to its exponent vector, which is an integer vector. And now we want to sort the monomials in our ring with the so-called degree reverse lexicographic term order. And we sort the monomials by sorting integer exponent vectors. So for two exponent vectors a and b, we say that a is bigger than b if the total degree of a is bigger than the total degree of b. And in case these total degrees are equal, well, then we take the difference of a minus b. And if the last non-zero entry of this difference is negative, then we again say that a is bigger than b. So now with this, you can sort monomials in your ring. And now given a polynomial, it's a sum of monomials. You can sort the monomials in a polynomial, and then you can extract the leading monomial. And with the leading monomial, we can already define a Gröbner basis. So we take a polynomial system I, and then we pick a finite basis G of our polynomial system. Yeah, and then we say that G is such a DRL Gröbner basis if the associated system of DRL leading terms of all polynomials in I is generated by the leading monomials just coming from G. Okay, well, this is a Gröbner basis. And we can compute them effectively via Gaussian elimination. So for this, we pick some input polynomial system F, and we fix a degree D. And then we set up the so-called Macaulay matrix. So for this matrix, we index the columns of this matrix with all monomials in our polynomial ring up to degree D. And additionally, we sort the columns with our degree reverse lexicographic term order. And now to index a column, we pick a polynomial f from our system and another monomial t, such that the product of t with f has degree less than d. And then in this row, t with f, t times f, we simply fill the coefficients of this product polynomial. And then we do Gaussian elimination of this matrix, and provided we make the D big enough, we will eventually produce a Gröbner basis in the row space of this matrix. And then the first D for which this happens, this is the so-called solving degree. And once you know the solving degree, well, then you can bound the size of the matrix, and then you can express the cost of Gaussian elimination with effectively with this binomial coefficient in the number of variables and the solving degree. Okay, so and another important quantity in this Gröbner basis complexity literature is the so-called degree of regularity. So if we take a single polynomial f, then f is again, it's a sum of monomials, and these monomials, they might have different degrees. But if we only keep the subsum of monomials of the highest degree, then we get, well, a homogeneous polynomial, which is called the highest degree component of f. Okay, and then given a polynomial system f, we say that it has a degree of regularity d if the vector space of homogeneous polynomials in degree d is generated by the homogeneous highest degree components of our input system f in degree d. Okay, and like as a culmination of a lot of like Gröbner basis theory, if your input system admits a finite degree of regularity, then you can prove that the solving degree is upper bounded like by a theoretical quantity from algebraic geometry known as the Castelnuovo-Mumford regularity. And this CM regularity in turn is upper bounded by a simple sum of the degrees of the input polynomials. Okay, and then, well, in the paper, we show that with very simple arguments, provided that your sample vectors A contain a maximally linear independent subset. So maximally linearly independent means that if you write the sample vectors in a matrix, then the rank has to be the dimension of the secret. If this is the case, then the degree of regularity is always finite for LWE polynomial system. Okay, degree of regularity finite. We have a solving degree upper bound. We can bound the complexity of Gaussian elimination for LWE polynomial systems to compute a Gröbner basis. Okay, and then you can evaluate this bound. And then, well, effectively you learn that for all kind of LWE instances, like general LWE, binary secret LWE, or small secret LWE, and small error LWE, you effectively get, how to say, exponential complexity estimate in the secret dimension. So, returning to Albrecht et al.'s analysis, they introduced this semi-regularity assumption. And if a polynomial system is semi-regular, then you can compute the degree of regularity with rather simple arithmetic. And the degree of regularity is a complexity measure for computing a DRL Gröbner basis. So And effectively, you can substitute the degree of regularity as a solving degree into the previous binomial coefficient. And additionally, the more polynomials you have in your input system, the lower this degree of regularity will become. So more input systems under more polynomials in the input system, lower complexity estimate under the semi-regularity assumption. So, and well, this property, while it's very intuitive, didn't show up in the proven complexity estimates. So, like, to bridge this gap, so we might have the impression, okay, more polynomials, lower degree of regularity. Is the degree of regularity at all a complexity measure of LWE polynomial systems if we drop this semi-regularity assumption? And the answer is yes, but we have to switch the algorithm or refine the algorithm a little bit. So again, we take an input system F and some degree D, and then we set up the Macaulay matrix in degree D for F, do Gaussian elimination, then we get the row space basis B1 of this polynomial system. Okay, now we set up a new Macaulay matrix for B1, do Gaussian elimination again, get the next row space basis. And now we iterate this process until this row space basis eventually becomes stationary. So that's our refined algorithm, and now we can define a refined solving degree, which is then the least D, such that this iterated process of Gaussian eliminations produces a Gröbner basis of your LWE polynomial system. And well, in the paper we prove that if a general polynomial system has finite degree of regularity, then this refined solving degree is indeed expressed in terms of the degree of regularity. And you can, as a worst case complexity, you can compute, well, the following complexity bound on these iterated Gaussian eliminations, which is more or less the same as before, or as Gaussian elimination on a single matrix, but with a higher exponent on the binomial coefficient. Okay, now returning to LWE, we have two approaches to complexity estimation. Yeah, we can work with this iterated process of Gaussian eliminations, where we know that the degree of regularity is a proven complexity measure, or we can return to Gaussian elimination on a single matrix. Okay, there the solving degree is just upper bounded by this theoretical Castelnuovo-Mumford regularity, but it turns out that the degree of regularity always lower bounds the Castelnuovo-Mumford regularity. So, and this is the first point where our worst case thinking comes into place, because if I were to evaluate a crypto system as a designer, I could say, well, when everything goes wrong, okay, the CM regularity on the right will become equal to the degree of regularity. And then I can throw in the degree of regularity into the binomial coefficient on the right and do my security evaluation. Okay, now, of course, the final question is, how do we get the degree of regularity when we don't assume that our polynomial system is semi-regular? And the theoretical answer is we compute a Gröbner basis of the highest degree component system, and the practical answer is this is impossible. So, and this is the second point where we introduce our worst case framework for complexity estimations. So, we take an LWE polynomial system where all error polynomials have degree big D. And then we want to generate the vector space of homogeneous polynomials in degree big D plus small d. And the basis of this vector space on the right, well, these are the monomials, the monomials in this degree. And this binomial coefficient on the right is the number of monomials in this degree. Okay, and then to generate the vector space on the right, we take our highest degree components of our input system, and we multiply them with all monomials of degree small d. And then we effectively do Gaussian elimination of this product. And then it's immediately apparent, well, the size of the product has to be at least, well, the dimension of the target space. Otherwise, we cannot have met the degree of regularity yet. So we get a very, very simple necessary condition on a, let's say, lowest theoretically achievable degree of regularity. And what we propose in the paper is quite simple. Well, given some LWE specification, we propose to evaluate this binomial coefficient to get an estimator on your lowest theoretical achievable degree of regularity. And then you assume, yeah, well, in the worst case, well, my true degree of regularity is going to be equal to my lowest achievable degree of regularity to my estimator. Throw this into the binomial coefficient of your choice, and then you do your security evaluation. Okay, and depending on your LWE instance, you can also significantly improve upon this necessary condition. So we can take a look at binary secret LWE. So in binary secret LWE, we draw our secrets from the set 0 or 1. So and then a priori, we can always add the polynomials xi squared minus xi to the system, because these polynomials, they just limit the solutions to 0 or 1. Okay, now we want to get the degree of regularity, which means we have to generate homogeneous polynomials in a certain degree. Okay, the monomials are basis of the homogeneous polynomials. And now we can have two kinds of monomials. Monomials that contain a square and square-free monomials. So if I give you a square-free, if I give you a monomial that contains a square, then trivially it's going to be generated by some xi squared, which is the highest degree component of this binary secret LWE system. So if we work with binary secret LWE, the only monomials that have to be non-trivially generated in your degree of regularity estimation computation are the square-free monomials. So in the binomial coefficient from above, we can replace this necessary condition with the necessary condition representing just the square-free monomials, which is this inequality. And if you take a close look to it, you are going to see that this inequality is always going to be much smaller than the one above. And now you can, just for sake of it, you can evaluate this inequality, or you can try to find the lowest achievable degree of regularity for, let's say, n to the power of d many samples. Then you realize that in a worst case scenario where everything goes wrong, binary secret LWE could have sub-exponential complexity with respect to Grübner basis algorithms. Okay, so now this is a lot of theory for complexity estimations that you might use or might not want to use. Now you could say, okay, let's throw this on our favorite LWE instance of your choice. So you can take a look at Kaiwa 768, and then you're going to realize that, okay, polynomial system solving, unfortunately for this LWE instance, is orders of magnitude away from what lattice algorithms can do. So only way you could improve or getting closer to lattice algorithm by introducing more samples. So let's say n to the power of 4 many samples, then you could, in theory, get close to what lattice algorithms can do. So this, of course, is good for Kaiwa. Okay, polynomial system solving will probably not break Kaiwa, but if you're a PhD student like me, trying to publish a paper in a major crypto conference, okay, that's not the most convincing argument. So how you can improve upon this? Well, you have to cheat. And so how do you cheat in practice? Well, so LWE crypto systems are very close to being released on the wild. So people start investigating them on sidechain resistant. So in previous work by Dachmann, Solid et al., well, they thought about, okay, which types of hints coming from sidechannel can we incorporate into lattice algorithms? And then they come up with 4 hints. And well, to make it short, because time is running out, of these 4 hints, one we cannot integrate into polynomial systems, and this is the last hint, which are short vector hints, because they don't involve the secret. But if we investigate LWE polynomial systems, then in principle, any kind of hint can be integrated into a polynomial system that can be modeled as multivariate polynomial. And if you're able to add a lot of low-degree polynomials to a LWE polynomial system, you might drive down the degree of regularity, which drives down the complexity, and then at one point you're going to say, well, under enough site information, I'm going to break my LWE crypto system. So, but for more details, I have to refer to the paper. So.
Okay. Yeah, thank you very much, Matthias. We have time for 1 or maybe 2 quick questions. So if you have any questions, please go to the microphone in the center of the room. This was your applause, by the way, not mine. Okay, is this a question? Yeah.
Hello, thank you for the talk. On smaller examples, where the system is found to be semi-regular or not?
Well, previous analysis reported it to be semi-regular. So Albrecht et al.'s work, they did experiments where they saw that it behaves kind of semi-regular. But Yeah, I mean, that's a bad question for me because, like in this work, I try to avoid working with the semi-regularity assumption at all. But the way I look at it is that the semi-regularity assumption is very strong because it's assumption on a sequence of polynomials, but people are only interested in the final sequence, and this is something which is typically not evaluated. They just care about the complexity estimate, and then they look at, oh, does in practice, my small scale experiments, do they meet the semi-regular estimate, yes or no? So,
yeah. Okay, let's thank the speaker again. So the next talk will be by Amedeo about crypto dark matter on the torus, oblivious PRFs from shallow PRFs and TFAG.
All right, thanks for the introduction. So yeah, before I start, this is joint work by myself, Martin Albrecht, Alex Davidson, who's in the audience, and Daniel Garden. Okay, so as an agenda, I'll first speak about OPRFs in general, so I'll give a definition and give you an idea of the post-quantum constructions that exist. Then I'll speak about our construction, in particular the non-verifiable one, and then finally I'll speak about how we suggest to add verifiability. Okay, so in terms of a plain OPRF, these are protocols between a client who holds an input X and a server who holds a server key K. And the idea is that in a round optimal OPRF, there's two messages, one request message and one response message, and at the end of the protocol, the client should learn the PRF evaluation, whereas the server ideally should learn nothing. So in particular, security asks, from the perspective of the client's input, it asks that a server should learn nothing from the OPRF request about the input, and on the other hand, the response should leak nothing about the server's key beyond the PRF evaluation that the client wishes to compute. Okay, so that's the plain OPRF setting. We can also consider variants of OPRFs. So the first one of note is the verifiable OPRF. So this additionally gives the client the guarantee that its output is in fact correct. So this stops a malicious server from deviating from the protocol in any useful way in order to force the client to accept a bad output. The other variant that we consider in the paper is a partial OPRF. I won't speak about this one in the talk though. And the idea here is that only part of the client's output is hidden, and you can just think of this as adding a public tag to the plain OPRF setting. So you add the public tag to that to the input and the request. Okay, so there are numerous applications. I'll not go into any details here, but if you want to see more, you can look at the references in the paper. Okay, so in terms of classically secure OPRFs, we have like very efficient constructions that simply send couple of elliptic curve points. However, in the post-quantum setting, things are slightly different. So what you'll see is that either you have good round complexity or good communication cost, and perhaps not both. A counterexample to what I just said might be the third row of this table. But one thing to note here is that the round complexity is 2 in quotation marks because it assumes some sort of correlated randomness shared between the client and the server. And in practice, in order to set this up, you would need to add more rounds of communication on. Okay, so a question that we wanted to tackle in this work is what can be achieved from FHE? In particular, can we get a round optimal, low communication cost OPRF from FHE? Okay, so in general, you can build basically any two-party computation, but in particular an OPRF from FHE using the following recipe. So the client would essentially sample an FHE key, encrypt its input, and produce a zero-knowledge proof that all of this was done correctly. It would then send a request that contains a bootstrapping key, an encryption, and a zero-knowledge proof. The server checks the proof, performs a homomorphic evaluation of the PRF circuit with the key hard-coded into it. And what happens at this point is the server obtains an encryption of the PRF evaluation that the client wishes to compute. And then the response would just be the ciphertext, which can be decrypted on the client side. So in terms of protecting the client's input, we have that the in-CPA security of the FHE scheme kind of obscures the input from the server. However, in terms of the security of the secret key, we need to do something called circuit private homomorphic evaluation. So in particular, normal homomorphic evaluation might leak details of the circuit that was applied. So we need to make sure that this doesn't happen, otherwise we leak information on the secret key. So to do this, we can use circuit private evaluation, which can be done using generic techniques or more specific ones, depending on the FHE scheme you're actually using. OK, so now that we've seen the general recipe, how do we pick the building blocks? So first of all, I'll introduce this crypto dark matter PRF, which actually suits FHE evaluation pretty well. So we'll see why in a few slides. But just to introduce the PRF itself, there are two public parameter matrices. These have entries that are integers modulo 3. And there's a binary secret key, binary matrix secret key. So when you want to evaluate the PRF on input x, what you do is you take your vector x, you do a mod 3 matrix multiplication using a public parameter matrix. You binary decompose that in order to stretch the length of that vector by a factor of 2. Then you do the secret key multiplication, which is a mod 2 matrix multiplication. And finally, you interpret the resulting vector as a binary vector with integers considered modulo 3, and do one more public parameter matrix multiplication. So considering the format of this evaluation, we can actually pass some of the work on to the client side. So in particular, everything before the secret key is applied can be done on the client side. And one thing to note here is that the zero-knowledge proof needs to take this into account. So it needs to prove that this vector y, this intermediate vector y, was computed properly. OK, now on the server side, it just has to essentially evaluate the remaining steps of the PRF evaluation. And as we'll show, this can be done relatively efficient using the TFHE scheme. OK, so hopefully you've seen FHE before, but I'll give you a brief idea of what the TFHE scheme does. So the TFHE ciphertext is just an LWE ciphertext. And in particular, this means that it's an additively homomorphic ciphertext up to a small growth in noise. The neat thing about TFHE in particular is it comes with this neat bootstrapping mechanism called the programmable bootstrap, or PBS. So the idea here is that as well as decreasing the noise of a ciphertext, you can also apply a function to the plaintext. In particular, this function has to have a property called negacyclicity. But in the context of binary plaintext space, this just asks that f of 0 equals minus f of 1. Okay, so it actually turns out that it's fairly easy to see that in the binary plaintext space, you can actually apply a PBS with a general function f by sort of decomposing the process into a negacyclic PBS followed by a linear shift. So for example, if we want to switch plaintext space, what we would do is we would apply a PBS with a function on this slide. And in particular, this is a negacyclic function considering a binary plaintext space. And then we just apply a shift afterwards. Okay, so this is essentially how you switch the plaintext space of a ciphertext using a single PBS. And yeah, one thing to note here is that PBSs are the expensive operation in TFHE. So you want to minimize the number of these as much as you can. OK, so moving back to the crypto dark matter PRF, we have the following sort of depth 1 homomorphic evaluation. So suppose you're given an encryption of binary value y. So you have a binary plaintext space. The first step is to do the matrix multiplication, which is just homomorphic additions. Then you want to consider that the resulting ciphertext as a ciphertext with a modulo 3 plaintext space. And to do this, you do the PBS, essentially one PBS per entry of a vector, where the PBS operation is described in the previous slide. And finally, you can do the last step, which is homomorphic additions, to implement the multiplication by G out. OK, so a few things to note, a few details. The circuit privacy actually happens during the PBS. It doesn't happen at the end of the homomorphic evaluation, at least using the techniques we propose. In which case, we need that Q, the modulus Q is divisible by 3. Otherwise, basically, the final ciphertext might leak intermediate values. All right, so in terms of performance, this is what you end up with when putting everything together. So we use various compression techniques. We also use zero-knowledge proofs from the client that are based on the lattice-based proofs. In particular, the LNP proof system from Crypto22, as well as Labrador from Crypto23. And this is what we get. So we get a bootstrapping key size, which is pretty big. This is like a problem, essentially a general problem with TFHE. So in particular, our bootstrapping key is 15 megabytes. However, we consider this an offline cost because you can send many requests with a single bootstrapping key. OK, so the client request size when sending a single query is around 46 kilobytes. But you can actually amortize this by essentially packing multiple queries into a single request message. And what you get when you do this is around a 2 kilobyte per query communication cost in the request. On the other hand, the server response is just 3 kilobytes. Another thing you can do is you can compress the size of the bootstrapping key at the expense of larger online communication costs. OK, so we also wanted to test roughly how long it would take to evaluate the PRF on a server, on a powerful server. So what we found was that using 64 threads and the parameters derived in the paper, we get a server response time of about 150 milliseconds. So one caveat to this is it doesn't actually implement the circuit privacy, and it also doesn't have a queue that's divisible by 3. Just because the library we use to implement this is called TFHERS, and these sort of cases aren't actually implemented as of today. OK, so adding verifiability can be done. So recall that the verifiability condition asks that the client can guarantee that its output is correct. So one easy thing you could do is you can add a zero-knowledge proof that the server did its computation correctly. However, the issue with this is if you want light verification and a good proof size, you actually need to pay a cost in terms of prover time. In particular, if you want to apply a snark or something, it seems that, well, currently it takes minutes for the server to compute this proof. OK, so instead we propose this cut and choose approach, which essentially entails the server publishing these public checkpoints. So these checkpoints are just inputs and outputs. And suppose the client now wants to send a batch of queries. So the queries are going to be denoted xj. Well, what it does is it copies these queries v times and then appends a bunch of checkpoints onto the end of this kind of long vector of inputs. And it shuffles these. So in this way, it obtains a vector we'll refer to as w. And it sends one request per entry of w. And then it gets back some responses where the server just crafts some sort of response, list of responses. And then the client can decrypt all of the responses and check for consistency amongst the vector of outputs. In particular, repeated inputs should correspond to repeated outputs, and inputs that are checkpoints should correspond to outputs that are correctly evaluated checkpoint outputs. OK, so in the normal setting, this is how you would run sort of this cut and choose approach. The problem in the FHE setting is that the server can actually do some sort of homomorphic equality test to potentially craft a sequence of responses that isn't correct, but passes all of the client's verification tests. So for example, one part of the homomorphic cheating circuit might ask that if you have an encryption of a WI, if WI is a checkpoint, output an encryption of the checkpoint output. OK, so if you have a full bootstrapping key, you can do this because you can essentially implement any circuit homomorphically. However, if you recall, we had a depth1 programmable bootstrapping circuit to evaluate the crypto.matter PRF. So we only need to give the server the ability to bootstrap in depth1. in which case we end up with an assumption that there is no depth 1 bootstrapping cheating circuit. So this is a heuristic assumption, and the depth of this assumption depends on the depth of the programmable bootstrap of your homomorphic evaluation for the PRF. OK, so using this kind of plausible assumption and some statistical cryptanalysis on the cut and choose method, we get the following. So if you want to batch 105 evaluations together, you basically get an overhead of 11 times in the online communication cost. So this is targeting 80 bits of statistical security and using the assumption from the previous slide. All right, so to conclude, I discussed the way you would use the crypto dark matter PRF and TFHE to build an OPRF. And the resulting OPRF has an online communication cost of a few kilobytes and fairly efficient server-side evaluation. However, the bootstrapping key is still a bit of a problem, but we kind of consider that as an offline cost. And to add verifiability, we use this cut and choose method, where the low depth of the PRF evaluation gives us a plausible security assumption. OK, so that's all I have, and thanks a lot for your attention.
Thank you very much. Amit, we have time for questions. So one question I would like to ask is this problem that it's hard to find the shallow circuit that performs the attack. Can you say something about what is known about the hardness?
So in a previous version of this work, we had a depth 2 circuit. And in fact, in depth 2, I think we had a circuit that would actually produce a cheating circuit. So actually, depth 1, you need depth 1 for a plausible assumption, it seems. So it's like a fairly tight security margin there. So.
OK, thank you.
OK, thanks.
OK, yeah, let's thank the speaker again. Okay, and the final talk of this session will be by Kelsey Jackson about the security of crystals dilithium in the quantum random oracle model.
All right. I suspect it goes without saying in this audience why it is important to develop schemes that are secure in what we would consider to be a quantum or post-quantum setting. But for those unfamiliar, what do we actually mean when we talk about a quantum setting? Now, maybe we start with a very familiar primitive. Here we have some hash functions. By definition, they must be deterministic, realizable, surjective. Good ones are also going to be efficient to compute, pre-image resistant, and collision resistant as well. Now on the left, we see a classical hash function mapping some arbitrary bit string to some n-length bit string. We then see on the right that we can construct a quantum accessible or a quantum hash function by permitting superposition queries and superposition responses to our classical hash function. Now, classically, a lot of proofs are actually solved in what we would call the random oracle model, which is basically where we replace any and all hash functions by these sort of idealized hash functions called random oracles. And here, our random oracles have all of the best properties for hash functions, but this is not up to some cryptographic assumption, but rather just automatically true. Now, specifically, in 2017, NIST, as you're likely aware, put out a call for schemes that are secure in a post-quantum setting. Their primary candidate for a digital signature scheme is called crystals dilithium. And it is secure to the definition and in the manner that they want, provided three problems are hard for quantum computers to solve. This is the module learning with errors, or MLWE problem, the module short integer solution, or MSIS problem, and self-target MSIS. Now, the first two problems in that list are pretty well studied and widely regarded to be secure, both classically and quantumly. But self-target MSIS was a completely novel problem to the design of this security scheme. So up until very recently, the exact hardness of this problem has not been terribly clear. So specifically what we set out to do in this paper was to prove the quantum hardness of self-target MSIS, and by extension, the security of dilithium under somewhat safer, better studied assumptions. Now, before we get into this proof, let's introduce just a few of the mathematical structures we'll be working with. First, we have RQ. This is the ring consisting of all polynomials with maximum coefficient q minus 1 and maximum degree n minus 1, as well as modular addition and multiplication operations. We can define S sub lambda, which is the set of all polynomials in RQ where the maximum infinity norm, or basically the maximum coefficient, is less than or equal to lambda. We also call these elements small elements of RQ. We also define B tau, which is the set of all short elements of RQ. These are polynomials where there are tau coefficients equal to 1, and all of the remaining coefficients are equal to 0. So with those now under our belt, we can define the modular versions of the problems that we will be working with. Here we have MLWE. In practice, you are given some operator A with elements in RQ, as well as a vector selected from one of two distributions chosen uniformly at random. It is either chosen from the uniform distribution over all vectors in RQK, or it is constructed in the form of an MLWE sample as seen here, where it is a product of A by some secret vector plus some error vector. These are generally selected according to some distribution D. Then the decisional MLWE problem, which is the one utilized by dilithium, is to identify which of these two distributions your vector has been chosen from. Now, obviously, we do see here that the hardness of this problem is heavily dependent on the distribution chosen. If D were the uniform distribution over RQK, the problem would be impossible. If it were, say, a delta function, it would be trivial. Now, for MSIS, we again have our operator A selected from RQ to the K by L. We are now aiming to find some small vector V, small but non-zero, such that A dotted by V is equal to 0. Which brings us at last to our novel problem, self-target MSIS. Here we once again have our operator. We also have some hash function. Since we are interested in the quantum random oracle model, we will assume that this hash function is chosen uniformly from the set of all functions from RQK to B tau. We then aim to find a vector with L minus 1 small elements and one final short element, such that the product of our operator by our vector hashes to the vector's final element, which is where we get that sort of self-target behavior from. Now, in order to prove that this problem is hard, we'll go through 3 steps, which I'll aim to sort of sketch out at a high level. First, we prove that solving self-target MSIS is at least as hard as solving some chosen coordinate binding experiment. We then show that this chosen coordinate binding experiment is at least as hard as solving a related collapsingness experiment. We then show that solving this collapsingness experiment is at least as hard as solving the MLWE problem with an error distribution that is uniform over S eta for eta function of Q, lambda, N, and L. So for step 1. So to begin, you might be aware of the classical proof technique called rewinding. We're going to talk about that very briefly here, where in practice you have some algorithm A that makes a number of queries to a hash function before outputting some sigma result and N, the query from which this result is formed. Now in rewinding, what you're able to do is sort of reset the circuit or rewind it back to an earlier state, say around the I-1th query, replace the hash function in its entirety with something that corresponds with the first I-1 queries, but may well respond to the later ones differently, and then run the circuit through again in order to produce a new output sigma prime. And specifically, Bellera-Nevin's general forking lemma would show that with non-negligible probability of success, we can find solutions that have different, like sigma, the actual solutions, but are constructed from the same query, n equal to n prime. Now, what this gives us, among other things, is that self-target MSIS is at least as hard as MSIS classically, where you are able to use this technique to generate 2 solutions to self-target MSIS, thus implying that the difference between the two is a solution to MSIS itself. But of course, this technique fails in a quantum setting wherein you cannot save an earlier state to rewind to without violating the no-cloning theorem, and you can't necessarily guarantee your ability to rewind after you have measured the initial sigma result. So instead, our first step to develop this proof was to find a version of rewinding that was more functional in a quantum setting. And what we found was called reprogramming. Here, instead of replacing the hash function in its entirety, you aim to reprogram it in a small, usually O of 1, number of places with the expectation that so long as the domain of H is superpolynomial, the odds of these substitutions being detected is basically negligible. And specifically, there's a result from Don et al. In 2019 as well as 2020 showing that you can use this technique to develop a quantum simulator algorithm, which we'll just call S, where it simulates the results of some P quantum query quantum algorithm, which we'll call A, with success probability delta S lower bounded by delta A over O of P squared, using only a single classical query or a constant number, in this case, a single one. So specifically, the first step of our proof is to apply this result and verify that if there exists any P quantum query quantum algorithm that attacks self-target MSIS with success probability like delta A, then it implies the existence of a one classical query quantum algorithm that attacks self-target MSIS with a success probability greater than or equal to delta A over 2p plus 1 squared. Now, if you were going to try to solve self-target MSIS while only allowed to make a single classical query, realistically, there's sort of only one way to go at it. In practice, you're going to choose some kind of query. Now, perhaps you do so in a very clever way, but you're going to have to pick one. Then the verifier will return some C. Since we are in the quantum random oracle model, this response will be chosen uniformly at random from the set B tau, at which point you try to design some small vector R such that the product of A by RC is equal to the query you've chosen, and again, R must be small. Now, if you're looking at the structure up here on the screen, this is actually identical to Del Agnol and Spooner from 2023's chosen bit binding or chosen coordinate binding experiments. Specifically, we generalized just a little bit farther into a module setting. But most helpfully, this means we have successfully shown that self-target MSIS is at least as hard as their chosen coordinate binding experiment. Further, we generalize their results to show that this chosen coordinate binding experiment is then harder to pass than a corresponding collapsingness experiment. Now, if we want to define a collapsingness experiment, what are we talking about? There are a number of different ones, of course. Now, here we're interested in some kind of experiment passed by a two-part algorithm, B1, B2, where B1 tries to construct some kind of register, which has to meet specific validity requirements, such that B2 has a better than random chance of detecting if a verifier has destructively measured the register. Now, if we are given some algorithm A1, A2 that passes our chosen coordinate binding experiment, we can use this to build registers over our query, vector, and response spaces, as well as potentially some register over just auxiliary memory, which we'll note as an arbitrarily length bit string. Then we can construct projective measurements that more or less just check whether or not the registers are in a self-target MSIS solution state. And in that case, if the B tau register is measured, in practice, it tends to perturb the states in such a way that they are less likely to be in a self-target MSIS solution state than if no measurement was made. Because of this binding property, the choice of that response B tau becomes very important to the structure of the state. Thus, using our initial algorithms that solve the chosen coordinate binding experiment, we're able to construct algorithms that solve this collapsingness experiment with greater than 50% probability, like initial success probability squared over 2. Which brings us at last to our third step, proving that solving this collapsingness experiment is at least as hard as solving MLWE for some uniform distribution. Now, When we talked about our collapsingness experiment, in practice, we're saying that any algorithm that passes that experiment must be able to distinguish between some identity operator and some computational basis measurement operator. And in turn, solving the decisional MLWE problem is about distinguishing between B, chosen uniformly at random, versus B taking the form of an MLWE sample. We can then construct operators of the following form. These are sort of partial measurements where you select some B, either an MLWE sample or a uniform sample, select a random S, then map Y to by plus S, rounded to the nearest of t values equally spaced over the allowed range. And in practice, what we're able to show is that the version of this operator wherein we use an MLWE sample is very similar to the identity operator, while the version of this operator wherein we use a random sample is very close to a computational basis measurement. Thus, our algorithm that is able to pass the collapsingness experiment and distinguish between I and MComp can successfully distinguish between the MLWE sample and random sample operators, and by extension, distinguishing whether or not B is an MLWE sample or a random sample, solving the MLWE problem. So, stringing all of these steps together, we come up with the final results here. If there exists an algorithm, any polynomial quantum query quantum algorithm that solves self-target MSIS with non-negligible advantage after p queries, then there exists an algorithm that can solve MLWE with advantage like the initial advantage squared over the initial number of queries to the fourth, where MLWE uses a distribution that is uniform over S eta, for eta as shown. We can then discuss more concretely how this affects the parameters that would be recommended for dilithium. Specifically, we look at the quantum core SVP security, which is just a very common way to quantify security of lattice problems in a post-quantum setting. And we would conclude that the quantum core SVP of self-target MSIS is at least as high as this function here of the quantum core SVP of MLWE, as well as P max, which is sort of the maximum allowed number of queries you allow for an attack on self-target MSIS. This allows us to come up with some conclusions, both generally as well as in comparison to the existing results for crystals dilithium. First, we provide the first proof that self-target MSIS is hard in the quantum random oracle model by showing that it is at least as hard as some version of MLWE. Then, if we compare our results to the original dilithium, on the con side, we do have some fairly serious increases to parameters. We increase the modulus Q from something like 2 to the 23rd to something at least 2 to the 40, though we settled on something closer to 2 to the 43. We increase the size of the public key by a factor of about 12, and the signature by a factor of about 4. However, with that said, we fully expected going into this project that we would have fairly serious parameter increases, just because the original specifications assume the existence of a tight reduction from MSIS to self-target MSIS, which was almost certainly not something we were going to be able to match. And this was purely a heuristic assumption, so there's no real reason to think that it is something we should be able to match. So while we do have these increases in parameters, we also provide rigorously provable security in a way that the initial specifications did not. In addition, there was one previous attempt to rigorously prove the security of dilithium, specifically by Kilt et al. In 2017. They called this formulation dilithium QROM. It did, however, require some fairly serious changes from the initial design, specifically by transplanting dilithium from its native ring to this new ring. So originally it was solved and sort of proposed over the ring RQ, where Q is equal to 1 mod 2n. But they instead proved the hardness of crystals dilithium over the ring RQ, where Q is equal to 5 mod 8. Now this has serious ramifications, both for how the mathematics of the ring itself works, as well as for how efficiently we can actually implement such a scheme. So very conveniently, when Q is equal to 1 mod 2n, we have this isomorphism where RQ is isomorphic to n products of ZQ. But when Q is equal to 5 mod 8, instead the best we can guarantee is that RQ is isomorphic to the product of 2 sort of rings ZQ over XN plus R for some integer R, and ZQ over XN minus R for that same integer R. This, among other things, precludes the use of the number theoretic transform, and instead requires the use of much slower algorithms when multiplying ring elements. As a result, while when we compare our concrete results to dilithium QROM, we do still see an increase in the size of the public key by about a factor of 3, and the size of the signature by a factor of about 1.5. However, we are able to prove the security of dilithium on a much better studied ring structure, one that we can be a bit more confident in its exact behaviors. In addition, we allow for a faster implementation of all of the algorithms that are used by the signature scheme, with approximately 2 times fewer integer multiplications and 3.5 times fewer integer additions for each use of those algorithms. So, very high-level conclusions. We prove that self-target MSIS is hard. We give a formulation of dilithium that is secure under sort of safer and better understood assumptions than the initial crystal's dilithium. And we give a formulation that is more efficient to implement in practice than Kiltz et al.'s dilithium QROM. And I would just like to briefly acknowledge my advisor, Dr. Carl Miller, as well as our co-author, Daoshen Wang, NIST Post-Quantum Cryptography Research Group, and the University of Maryland. I would now like to answer any questions you may have.
Yeah, there seem to be some questions, yeah.
Thanks for the talk. So maybe this is a clarification question. Maybe I skipped some part of your talk. So in your proof roadmap, so if I understand correctly, in your reduction from self-target MSIS in the QROM to the CCB experiment, so this is the step where you're using some QROM proof techniques. Mm-hmm. And CCB, if I understand correctly, it's a completely classical experiment, and you're not modeling any hash functions in the CCB experiment, right?
No, there are no hash functions modeled in it. I'm not sure I'd describe it as strictly classical, but specifically we're just generalizing the chosen bit binding experiment that Delagnol and Spooner proposed to sort of a module setting, and we've called that the chosen coordinate binding experiment.
Yeah,
because,
but in the specification of the experiment, there's nothing quantum going on, right? I mean...
yes, I agree. You've moved outside of the hash function.
Yeah, and the MLWE is also a classical experiment. So can you? But the collapsing experiment that you use in between, again, there's something quantum going on. So you pass a quantum state. So.
Well, I guess why I wouldn't call it just a classical experiment is because while the experiment itself may involve sort of classical steps, we are allowing quantum algorithms to attempt to solve it. Mm-hmm. We are suggesting that the existence of a quantum algorithm attacking self-target MSIS implies the existence of a quantum algorithm attacking the chosen coordinate binding experiment, implies a quantum algorithm solving the collapsingness experiment, implies a quantum algorithm attacking MLWE.
Okay.
I agree you move outside of the quantum random oracle model specifically, but that doesn't necessarily mean that you've moved outside of the realm of sort of quantum computing broadly.
But isn't CCB using black box use of this quantum adversary? So, okay, I mean, maybe I'll...
yeah, I'm happy to talk about this more with you later if you'd like.
Hi, thanks for the nice talk. I guess I'll ask the obvious question. Is there any hope of getting a tighter reduction and smaller parameters?
Yes, we absolutely think that that's feasible, and it's something we've continued to work on. Sort of our next big moves will be aiming to tighten this further and aiming to see whether it can be generalized and these techniques can be applied to other signature schemes that are post-quantum and based upon the Fiat-Shamir transform.
Perfect, that was my second question. Thank you.
Lovely.
Quick question, quick answer, please.
Hi, my question is, usually MSIS is defined with the Euclidean norm, and as such, could you have the same reduction without losing tightness like with the square of the dimension going from the infinity norm to the Euclidean norm?
Yeah, we haven't explicitly explored the change in norms just because we were choosing to study what was used in dilithium, which is the infinity norm. But there are some very interesting differences in the security reductions for the different norms on these problems. So that would absolutely be a valid thing to look at sort of for our next projects on these subjects.
Okay, thank you.
Mm-hmm.
Okay, so let's thank Kelsey and all speakers of the session again. And we will now have the coffee break and the Eurocrypt meeting. So, enjoy.